In this video, we're going to be looking at exponential equations. Part 1, we're going to be looking at the type of exponential equation that we can use the same base. An exponential equation has the variable in the exponent. The x is in the exponent. And the easiest way to solve them is if we can get the same base on both sides, so we can equate the exponents. In part 2 of the video, we will see that that is not always possible and we'll have to use logarithms. So you can choose. First of all, our process here is we're going to isolate the base. We're going to attempt to rewrite each side of the equation with the same base, and in these next few examples that will be possible. When it's not, we'll have to use logarithms. Then we're going to equate the exponents and solve. So in this first example, we have 2 to the x is equal to 16. So we've isolated the base. The base is the one with the exponent. Then we want to rewrite each side of the equation with the same base. Meaning, how can I express 16 as 2 to a power? 2 raised to what power is 16? It's 4. Convince yourself that's correct. Now, because the bases are the same, the exponents are equal, and we have solved. So 2 to the 4th power is equal to 16. Now that's pretty easy. Probably didn't even need to write out all those steps, but it will get a little more difficult. So let's look at the second example. Can we get 4 and 64 in terms of the same base? I think we can. So I'm going to keep this side the same. And then I'm going to think, okay, well 4 squared is 16. What's 4 to the 3rd power? That's 64. So I can rewrite 64 as 4 to the 3rd power. Now I can equate the exponents, because if the bases are the same, now the exponents have to be equal. And now I just need to do a little algebra to solve for x. So let's add 1 and divide by 2. So we can come back up here and check and say 4 to the 2 times 2 minus 1, does that equal to 64? Well, yes it does, because that's 4 minus 1 is 3. You don't have to check, but that is how you could check. Now the third one, a little bit harder. Okay, so they have exponents on both sides, so that's good that they're separated or they're isolated on each side of the equal sign. But we need to rewrite them in terms of the same base. So you always want to think about the smaller number. So 8 is smaller. Can I express 8? Can I get 16, in terms of 8? Well, 8 to the 1st power is 8. 8 squared is 64. So I don't think base 8 is it. Can I go something smaller? Well, base 4? No, 4 squared is 16, can't get to 8. Go smaller. What about 2? I know 2 cubed is 8, and 2 to the 4th power is 16. So what I'm going to do is I'm going to take these two bigger numbers and express them with the base 2. So 16 is 2 to the 4th power. I'm going to replace that and leave the x minus 1. 8 is 2 cubed. Replace 8 with 2 cubed, but leave that exponent. So I've got them to be the same base. But before I start equaling the exponents, let's use our properties. I can multiply those. So that's 4x minus 4. Don't forget to distribute. This is 3x plus 9. Now the bases are the same. Now I can set those exponents to be equal to each other and solve for x. So if I subtract 3x and add 4, I get x is 13. You can check that out. Calculator might be helpful. That was a little bit harder. Again, you have to think about the same base. Always go smaller, not bigger. This one's probably not as hard, except that you've got them kind of reversed, as in one's in the denominator, one's not. Let's look at 49 and 7. What could be the common base? That's what we're looking for, a common base. Well, 7 to the first power is 7, so that's good. And 7 squared is 49, so I think 7 is the right base. So let's take 49 and write that as 7 squared. But here, we don't want 1 over 7. What takes the reciprocal of the base? A negative exponent. So 1 over 7 is the same as 7 to the negative 1 power. So again, we can multiply that. Now I have the same base. Now I can equate the exponents and solve for x. This example is actually pretty easy because the e is the base. You don't have a choice. E is your common base. So you have e to the 3x plus 2. The only thing you have to do is you have to flip that, just as in the last example. So instead of positive 3, we make it negative 3. Remember, 1 over e cubed is the same as e to the negative 3. Keep the base, take the reciprocal of the base, change the sign of the exponent. So now the bases are the same. Now we can equate those exponents and solve for x. Let's look at our last example. So we have 9 and 27. Common base. Well, again, think small. 9 to the first power is 9. 9 squared is 81. That's too big for 27. So think about a smaller number that might work. What about 3? Well, we know 3 squared is 9 and 3 cubed is 27. That'll work. So I'm replacing 9 with 3 squared. I'm replacing 27 with 3 cubed. And remember, we've done this before. What's that square root as a power? The half power. Now we're going to multiply those exponents. So we have 3 to the 4x minus 2 and 3 to the 3 halves. Now our bases are the same. So we can set our exponents equal to each other. Now at this point you can deal with the fraction. You can make it 1.5, although I kind of cringe to say that. We could just multiply everything by 2 to get rid of that fraction. Just make sure you distribute. So let's see if I add 4 and divide by 8. So again, if we can get them to be the same base, we want to isolate the base, rewrite each side of the equation with the same base, equate those exponents, and then solve. What happens when you can't get it to be the same base? Then we have to use logarithms. That's in the next video.